Now we're going to start talking about length of curves. I drew a picture here, best I could using Word. We have this curve here that's in blue, and we're going to estimate it by little segments. Each one of these segments can be found to give an approximation. How can we find that segment? We could say this is delta y sub k and delta x sub k. Then the length of the segment would be, using our Pythagorean identity, delta x sub k quantity squared plus delta y sub k quantity squared, and the square root of that. Now, what are we going to do in order to find the length of the curve? We're going to have to sum all of those up. So we have the sum, delta x sub k squared plus delta y sub k squared, and then the square root of that. And eventually, we should be thinking right now of a Riemann sum. Let's review for a second what a Riemann sum is. That would be the limit as the norm goes to 0 of the sum of f of c sub k times delta x sub k. So our goal is going to get this to manipulate to look like that. Well, we don't have that right now. We don't have that delta x sub k. There's multiple different ways you could manipulate this. One of them is to take that and we will divide it by delta x sub k. Let's just go ahead and copy that over. And if we divide it by it, we have to also multiply it, right? Because we're just doing a clever form of 1. When we bring that inside the radical, since this is it's positive there, it's okay to do, we will end up getting 1 plus delta y sub k. When we bring it in, it'll end up being squared, so we can bring that inside this square, and we'll have delta x sub k quantity squared, let me extend that down, and then times delta x sub k. So right now, this part looks good. We have that delta x sub k just like we have it here, but we're looking at f evaluated at some value here. We need to be f of some number inside the interval. What is this? Go ahead and write that down on your paper, that this is the average rate of change over an interval, right? It's a slope. It's a secant slope. So we want to be able to relate that secant slope to a point, a slope at a point, or just something at a point. It'll be a slope. What theorem should you be thinking of? Yes, it's the mean value theorem. What does the mean value theorem say? If a function is continuous on a closed interval and differentiable on the open interval, there exists some value in the open interval where the instantaneous rate of change equals the average rate of change, or the derivative at the point equals the average slope over the interval. So we will apply that here. Let's say, oh, I forgot to say over here, this proof is based on the fact of the curve being smooth, which means it has a continuous derivative. So if it has a continuous derivative, it is differentiable. So we can say, using the MVT, let me put that a little bit lower. We have, there's some c sub k in the kth interval, we'll say x sub k minus 1 comma x sub k, where f prime of c sub k equals delta y sub k over delta x sub k. So when we apply that here, we will have the sum 1 plus f prime of c sub k quantity squared times delta x sub k. Now that's looking a lot like this. This would be, we have a finite sum. We want to find the limit of this as the norm goes to 0. Remember, the norm is the largest subinterval. And then we will get our exact length of the curve. call it here L, and that's going to equal, so since this is an x, we're using in terms of x, we have to have x numbers. We're going to be going from a to b of 1 plus f prime of x quantity squared. Again, let's make sure that's there. And then the delta x goes to dx. Another way to write that would be from a to b of 1 plus dy dx quantity squared, again extend that down, dx. And so this would be if y is smooth, or a smooth function on the closed interval from a to b. You can repeat this and go through the exact same steps, but instead of divided by delta x sub k, we'd go delta y sub k, and when we repeat it, we could say, or L equals the, in terms of y, it'll be from c to d of 1 plus g prime of y quantity squared dy, or probably a better form for us to write it is 1 plus dx dy, so we're taking the derivative of x with respect to y, and then dy. And this is if x is a smooth curve or a smooth function on the closed interval from c to d. All right, now let's look at some examples applying this. Oh, I forgot to use my picture. This was supposed to be showing the MVT. So we have x sub k minus 1, c sub k, x sub k, and we're saying somewhere on that interval that instantaneous rate of change, the slope of the tangent line equals the slope of the secant line. That's always a good thing to review. All right, now the examples. So we're going to find the length of the curve of y equals 2/3 x to the 2/3 from 0, 0 to the point 1, comma 2/3. We have a function in terms of x. Let's go ahead and find the derivative. dy dx equals 2/3 times 2/3, which will give us 4/9. And then we're going to go 1 minus 1, so negative 1/3 would be our exponent. So we can say L equals the integral, we have x numbers, we're going 0 to 1, of 1 plus this there, so we'll put 4/9 x to the 1/3 quantity squared dx. I'll come over here to continue simplifying this. Now what we're going to do is just manipulate it. So we'll say 0 to 1 square root. This part here is going to give us 16 over 81 x to the 2/3. So I'm going to get a common denominator. I'll have 81x to the 2/3 on both the top and the bottom, since this has to be the same as 1. At this point, I can factor out the 81x to the 2/3, which will end up giving 1/9 x to the 1/3, and we have a positive interval here, so x to the 2/3 square root of that will be positive, and we don't need to worry about absolute value or plus or minus there. Square root of 81x to the 2/3 plus 16 dx. Now, at this point, you can do it either way that I've shown in class. We could do a substitution, and I'll show that because some people seem to really want to see that. But you could also force the substitution or make the substitution by pulling out the 1/9. We know the square root of the inside part would be 81 times 2/3, which will end up giving us 54. So we could put a 54 on the top and a 1 over 54 on the outside. But I'll go ahead and just do the substitution. Oh, we have the derivative on the outside of the variable as well. And then du would end up being 54x to the negative 1/3 dx. So if we substitute that in, move that 54 to the other side, we'll have, I'm going to pull out the 9, the 1/9 part, and then we'll have, I should change my limits. Always change your limits. If you're going to go and you have a definite integral and you do a substitution, go ahead and just change it immediately. So we'll have from 16 to 97, and I could pull out that 154 first, or I could say, yeah, I'll just do that here, because we're going to have 1 over 54 du, and then we have square root of u du. And at this point, this is a pretty straightforward integral, so we have, multiply all that junk out, you get 1 over 486, and then u to the 3/2 times 2/3 from 16 to 97. It's not going to simplify really nice, but that's okay. 2/3 of that will end up being 1 over 729. 97 to the 3/2 minus 16 to the 3/2. Can't quite squeeze it in there. So we'll have 1 over 729. 3/2 is the same as 1½ So we have 97 times root 97 minus square root of 16's 4 cubed would be 64. And that would be the length of that curve. Let's look at another one. This time we have x in terms of y. A common mistake that some students make would be to try to get this in terms of y in terms of x. We already have x in terms of y, so let's use the other form. So this time we're going to find dy, instead of dy dx, we'll find dx dy. So we'll bring down the 3/2. That will simplify with the 2/3 to give us 1. Write it just to show it. And then we have y minus 1 to the 1/2. So we have, simplifies nicely here. We can say L is, this time we're dealing with our y numbers. Everything will be in terms of y, so we're going to go from 1 to 4 of the square root of 1 plus y minus 1 to the 1/2 quantity squared dy. Last one was a little ugly. This one works out kind of nice. We have y minus 1 dy, so all we have is the square root of y dy. And you know what that is. We just basically did the same thing. Y to the 3/2 times 2/3 evaluated from 1 to 4. So we get 2/3 times the quantity of 4 to the 3/2 minus 1. 4 to the 3/2, square root of 4 is 2. Cubed is 8. 8 minus 1 is 7. So we get 14/3. So the length of this curve from point A to point B is 14/3. Let's take a look at the last two. These ones will be a little bit more involved. So we're going to find exact same thing. We have this time we have y in terms of x again, so we'll find dy dx. I try to write a little bit smaller because I'm going to need some space here for this manipulation. Bring down the 3, we'll have 1/2 x squared minus, bring down that negative 1, 1/2 x to the negative 2. L, we're in terms of x, so we're going to go from 1 to 2. 1 plus x squared, I just throw it over 2, minus 1/2 x to the negative 2, quantity squared dx. We need to multiply all that stuff out. So from 1 to 2 of the square root 1 plus x to the 4 over 4. And then we'll have 2 times this one times this one. Well, the x's are going to give us x to the 0. And then we have just minus 1/2 plus x to the negative 4 over 4. Now look what happens there. We have this part here came from squaring that, and the only difference now we have is 1 minus 1/2, so we have a plus 1/2, and there is our big hint for how to factor this. So that is just going to be the square root of the exact same thing we had before, x squared over 2, but this time it's going to be plus x to the negative 2 over 2 quantity squared dx. Square root of the square will give us the absolute value, but this is a positive. We could take a look at the graph, take a look at the values. It is positive on that interval. So we have from 1 to 2 of x squared plus 2 plus x to the negative 2 over 2, and now we can go ahead and integrate. So this would end up being x cubed over 6 minus 1/2 x to the negative 1 from 1 to 2. Plug all that stuff in. 8/6 minus 1/4, that quantity minus 1/6 minus 1/2. Put all my equals, and that simplifies to 17/12. So that one's a little more involved, but still the basic stuff, you can follow through with that. And let's do one last one. This one looks a little uglier. Here's a hint. When we look at these points, we have these ugly fractions for x. We probably want to try to get it in terms of y. And when we look at this, we have just an x here, but we have y to different powers. So we do want to solve this equation for x. So we'll say 30xy cubed equals y to the 8th plus 15. Divide by 30y cubed, so x is going to equal 1/30 y to the 5th plus 1/2 y to the negative 3. Now that we have x in terms of y, go ahead and find the derivative of this with respect to y. So we get 1/6 y to the 4th minus 3/2 y to the negative 4. That's kind of the basic part of this. At this point, it's very similar. So we'll go y numbers from 1 to 2, 1 plus 1/6 y to the 4th minus 3/2 y to the negative 4th, quantity squared dy. Multiply all that stuff out. 1 plus 1 over 36 y to the 8. Look what happens again. The exponent of y will be 0, and so we're just going to end up getting 1/2 again. Plus 9/4 y to the negative 8 dy. Simplify that. The 1 minus 1/2 will give us our positive half, so we have 1 over 36 y to the 8 plus 1/2 plus 9/4 y to the negative 8. You can factor that. The exact same thing we had before, except this time it's positive. 1/6 y to the 4th plus 3/2 y to the negative 4, quantity squared. Integral from 1 to 2 still. 1/6 y to the 4th plus 3/2 y to the negative 4. That quantity, square root of x squared, or this quantity squared, just gives us the quantity. Now we can find the antiderivative of this. 1 over 30 y to the 5th minus 1/2 y to the negative 3. Evaluated from 1 to 2. So we'll plug that in. 32 over 30 minus 1 over 16 minus 1 over 30 minus 1/2. You can get a common denominator. This would be 16 over 15. That'd be 240. So we'll have 256 minus 15 minus 8 plus 120, and we get 353 over 240. And that's it for finding the length of a curve. Now, one of the things, there's not much room here, so go ahead and write this on the other side at the bottom of your sheet. Sometimes a function is not differentiable with respect to x, but it is differentiable with respect to y. So you would have to use that second form, solve it for y, and then proceed as we have on the second examples. An example of that would be something like y equals cube root of x, some interval that includes 0. It's not differentiable at 0, but if you solve it the other way, you can get x equals y cubed, and now you've changed that vertical tangent to a horizontal, and now you can proceed. And that's it.